a lot of very serious scientists really don't understand what's going on. And it's just a case of accepting where we've got to with science, and accepting that science can't actually give us all the precise answers that we're accustomed to. So this is a little bit of a tribute to Richard Feynman, who's probably one of the finest theoretical physicists of the last century. I'm a little bit uncomfortable that he worked on the Manhattan Project, but that aside, this is a quote directly from Richard Feynman. Anyone who claims to understand quantum theory is either lying or crazy. Okay? And if you take anything away from today, it's an understanding that scientists really don't have all the answers. Okay? And nature behaves in a very strange way at the microscopic level. So, we're going to start with things that we understand. Human beings like to relate things to what they observe in everyday life. And physicists put things into roughly two categories. There's particles. This is an enlarged particle. Anyone here play cricket? Yeah. Yeah? Catch? Oh, clearly not. You can throw it back to me if you like. You can throw it back. Right, so particles are, sort of indivisible, if you like, indivisible objects. They can bounce. They can, you can feel them. They're tangible objects. Waves, on the other hand, are a bit different. So, David, do you want to come over here and hold the string for me? Okay, so if David shakes the string up and down, maybe a bit more vigorously on a regular basis, do you know how to produce a wave? Has anyone ever told you how to produce a wave? Right, I'll show you. Right. So this sort of idea, waves are, if you like, wavy. Okay, let's stand over here so people can see a wavy wave. And there's sort of this idea that, we can't actually pinpoint where the waviness of this wave is. Okay, so waves are a very different kind of animal, if you like, to particles. Thank you, David. So what scientists, especially physicists, like to do is put things into one of these two categories, because these are things that we're familiar with, and we can work things out with them. Now, one of the things that's very specific to waves is this idea that waves do funny things when they meet each other. They do what we call interfere. So because I don't have a water tank here, I'm going to show you a simulation of what happens. This is a dripping tap, and you're looking at this from above, and it's dripping onto water. And here you've got a couple of slits, and the water's sort of being forced through these slits. And what you can see happening here are a series of dark and light patches. And if we say, for the sake of argument, that the light patches are like the top of a wave, which we normally call a crest, and the dark patches are the bottom of a wave, which we normally call a trough. What happens is, when a crest meets a trough, you get nothing. And when a crest meets a crest, it reinforces, and when a trough meets another trough, it reinforces. And you get this nice pattern. And that pattern's called an interference pattern. And it's very particular of what happens when waves meet each other. These don't do that. They like to stick to themselves as particles. So particles don't interfere, but waves do. So what I'm going to talk about today is a thought experiment attributable to Richard Feynman. And the good thing about a thought experiment is this: money's no object, okay, and we can be as outrageous as we wish to be, and see what happens when we think things through logically. So I'm going to give you a little bit of a brief history of where these ideas have come from. So back in the sort of 400 years ago, I don't know what century it was 400 years ago, historian, what century was it 400 years ago? 17th century, okay. Isaac Newton, who was the preeminent scientist at the time, decided that light behaved as a particle, behaved like one of these. Okay, he called them corpuscles of light. And every model that they put together seemed to fit Newton's theory, except for one or two anomalies that I won't go into. And then, round about the early 19th century, another British physicist called Thomas Young did exactly the experiment you saw with water, but did it with light. And when he did it with light, he proved that you could get these nice interference patterns. And so the model changed again, and people decided that actually light is a wave. And then round about the turn of the 20th century, Albert Einstein analysed the very famous photoelectric effect and decided that light was a particle. So, is light a particle? Is it a wave? Or is it a particle? Nowadays, we talk of light as something called a photon. But what is it? Is it a wave? Or is it a particle? The answer is we don't actually know what it is. What we're trying to do is we're trying to force nature into one of these two categories. But the reality is, nature doesn't work that way. Some people like to use the word wavical, but the answer is we don't know. I'll give you another example. Here's a brief history of electrons. You should all know about these because you'll have done them in GCSE, but around about the 19th century, J.J. Thomson, another British physicist, in fact, you'll probably notice that all these British physicists are white men. I don't know why, but maybe we can change that. So J.J. Thomson discovered the electron. The electron was very much a particle. And then, round about the mid-20th century, these two guys discovered that electrons behave like waves again. So again, are electrons waves or are they particles? Answer, we don't know. So what I'm going to try and analyse today is this idea that nature behaves in a mysterious way which we human beings have failed to actually come to terms with. We've failed to come to terms with the fact that nature at the tiny, tiny level doesn't behave in a way that we're accustomed to. And so we sort of put our hands up and say we don't know what's going on. So I'm going to describe an experiment with bullets. This was an experiment which has never ever been performed before. But the thought experiment has been analysed several times, initially by Richard Feynman. So this is what we're going to do. We're going to try and do what we did with the water waves, where the tap was dripping and there were two slits. Except this time, we're going to fire bullets at these two slits. And we want to see what happens at the other end. So, we're going to make some assumptions. We're going to use indestructible bullets. In other words, these cannot possibly end up splitting in half. They stay as solid objects. So that's the first assumption. We're going to fire them from a machine gun that's not a very good machine gun because it sort of sprays them with a bit of an angle. And they're going to pass through this armoured plate. This is an armoured plate, so it's not going to be damaged in any way, but there are two slits in the armoured plate. And then here we've got a backstop. It's a screen where we can count the bullets. You can imagine it's like a sandbox. And the bullets fall into the sandbox, and at the end of the day, we pick the bullets up and we can count them. Okay? We're going to plot a graph. Ooh, Susan, very scary. We're going to plot a graph, okay, of the average number of bullets per unit time. That's from Monsters vs. Aliens. Ooh, Susan, I'm scared. Doesn't matter. If you haven't watched it, so it's just lost them. Right. And then we're going to repeat the experiment by closing one of the slits and then closing the other slit. So I'm going to talk you through that logic, and we're going to come up with what I think should be a fairly sensible conclusion. So, these are the results of the bullet experiment. So, this is what happens. Here's the source of bullets. This is an aerial view. These are the two slits. I've affectionately called the slits slit number 1 and slit number 2. This graph here, N1, is the number of bullets per unit time I get from slit 1. In other words, if I close this, you would expect that most of the bullets fall round about here. And over here you don't get very many. And then if I close this slit, I get this curve, which I've called N2. This is the number of bullets per unit time from slit number 2. And as you can imagine, most of the bullets fall in this area. And then this graph, which I've called N12, is the graph that you would get when both slits are open. And as you can imagine, again, you get a bit of a hump here, maybe a few less over here, and then another hump over here. Okay, so what do we conclude? The first thing we conclude is that bullets do arrive in lumps. And the reason we know they arrive in lumps is the following. If we count how many arrive here from slit number 1, and then we count how many arrive here from slit number 2, and we add them together, we get this graph. You never ever get 2 bullets arriving at the same time. In fact, you might say to me, yeah, but if the bullets go really fast, maybe you get bullets arriving at the same time. So what we'll do instead, because it's a thought experiment and we're allowed to do this, we'll slow the machine gun down so that the bullets arrive distinctly. Right? So the bullets arrive in lumps. You never get 2 bullets arriving at the same time. And this is the law that we come up with. The bullets that arrive when both slits are open, which is this graph, is actually the sum of these 2. And we say that this curve doesn't show any interference at all. Right? This looks nothing like what we get with a pattern with waves. Okay? That's the result of the bullet experiment. Just note that although bullets arrive in whole numbers, because this is the number of bullets per hour, this doesn't have to be a whole number. So for example, if we get 25 bullets in 10 hours, that's 2.5 bullets per hour. Okay? You all comfortable with that idea, with averages? Yeah? Average family has 2.2 kids, that kind of thing. Doesn't mean there's a family with 0.2 of the kids somewhere, just it's an average. Yeah, okay, good. Right, so much for bullets. They arrive in lumps, and they don't show any interference whatsoever. We're now going to do the same thing with waves. Now, I've actually shown you what happens with waves. When you've got 2 waves together, you get this nice ripple effect. So the point about waves is, unlike our particles, remember, they can have any size at all. They can be any height we choose them to be. They're going to pass through the plate with 2 slits again, and we're going to detect on the screen the intensity that we get when the waves arrive. And we're going to plot a graph of the average intensity per unit time, just like we did with the bullets. And then we're going to do the same thing. We're going to repeat with 1 slit closed and the other open, and then reversed. Oops, that shouldn't have happened. So this is the pattern that we get with waves. So the waves start here. This is our source. It's an aerial view again. 2 slits. If I close one of the slits, I get the same thing that I get with bullets. Okay, the intensity happens to be greatest where the slit is open. That's N1. When I close this slit and open this one, I get this curve. So it's more intense from what comes out of slit 2. The interesting thing about waves is when both slits are open, you get this funny looking curve here, called an interference pattern. Okay. Waves display interference. And this time, N12, which is this curve, is no longer the sum of these 2. It's a more complicated relationship. Those of you that enjoy the maths, it's actually the square of the sum of the amplitudes, but let's leave that to one side. This is nothing unusual, right? This is a wave phenomenon. It's what I showed you earlier on the simulation. And if you actually looked at the screen head on, you would see these patterns, bright, dark, we call them fringes. Oops, everything's frozen. Right, so much for waves. Waves display interference, bullets don't display interference. These are things that we are comfortable with in everyday life. We can see, touch, feel waves. We can see, touch, feel particles. We're now going to collapse everything down to the microscopic level. So we can't actually see these things now. At the microscopic level, we're talking about things like an electron, which I mentioned earlier, or light, which we believe is now made of photons. And we're going to do the same experiment. Now, electrons can be generated using what's called an electron gun. We'll leave the physics to the physicists, but essentially you can fire electrons at a screen and you can see a little flash of light where the electrons hit the screen. Old-fashioned television screens used to work like this. So we're going to do the same thing. We're going to take our electron gun and we're going to fire the electrons at 2 slits, and then on the back we're going to count the electrons and see what sort of pattern we get at the back. The first thing that you need to know is that every time the electron hits the screen, we see a flash of light or we can hear a click. If it's not a photosensitive screen, we can use a tube, like a photomultiplier tube, and you will hear a click. It might go click, 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 like that. But we can definitely hear the electrons arriving. The electrons arrive in lumps, just like the bullets. We can turn the source down like we did with the machine gun, and we can make sure that the electrons never arrive at the same time, so they arrive individually. What do we see? So this is a bit like the bullets experiment. The electrons are indestructible. They arrive in lumps, they're individual. What do we see? That's what we see. That looks just like the waves. Okay. We see something that looks just like the waves. And if we close down this slit, we get this curve. If we close down this slit, we get this curve. And when both slits are open, we get this interference curve. This is odd because the bullets or the electrons, they're arriving in lumps, but yet they're showing an interference pattern. And what's more bizarre is this, that somehow opening both holes lets fewer electrons through in certain positions. So these are the points where you've got like nothing coming and a lot coming, nothing coming and a lot coming. Well, hang on, when only slit 1 was open, we got a huge amount of electrons here, and yet at this point we're getting nothing. It's pretty odd, but I think it's very, very odd. It's quite disturbing. If we turn the source right down so that the electrons are arriving one at a time individually, and you wait long enough for the picture to build up, this is what it's frozen again. This is what you would see. So initially you would see a scattering of dots, and it looks quite random. But as you wait long enough, this is the pattern that builds up. You see these bright and dark patches. So, our electrons are behaving like waves, even though we know they arrive in lumps. And even though we know particles don't interfere. It's a bit screwy, isn't it? It's just odd. Very, very odd. So, this is the peculiarity. Let's make a proposition. All scientists like to make a good proposition. So the proposition is, the electrons must either go through slit 1, or they must go through slit 2. Let's have a look at the apparatus again. Yeah? We've got 2 slits. The electrons arriving individually. They've either got to go through that one or that one. They can't go through both at the same time. It just can't happen. So that's our proposition. We can see from the result, which was this result, that clearly that proposition is false. maybe the electrons split in half and they go around both holes. But we know that can't happen because the electrons are indivisible. So what do? We've got to the point now where we really, really don't know what to do. So I'll tell you what we'll do. What we'll do is we'll actually watch them. We'll watch what happens as they go through each slit. Because if we can do that, then we'll know for sure, won't we, whether they go through one hole or the other hole. So this is what we do. We put a light source right next to these slits. In fact, we can put more than one. And that little light source will glow every time an electron passes through each of these holes. That's what we get when we turn the light on. The interference pattern has disappeared, and it looks exactly the same as you would see if you fired bullets at the two slits. Turn the light off, you see that. It's almost like the electrons don't like being watched. If you watch them, they behave like bullets. If you don't watch them, they behave like waves. It's very frustrating. This incidentally has been done, and this is exactly what we get. So we say to ourselves, right, this is ridiculous. Tell you what, maybe electrons are really delicate and the light just bombards them. In fact, we have to conclude that light definitely affects our result. The electrons are very small, after all. So maybe we should use a weaker light, because if we used a weaker light, it won't disturb the electrons as much. In fact, this is a picture of the famous Compton effect. This is light hitting the electron, and the electron just bounces off as a result of a collision with a photon. So maybe if we turn the light down so it's really weak, so it just barely disturbs the electrons, maybe we'll get to the bottom of this weird story. So, consequences. If the light is really weak, there will be occasions when we don't see a flash at all. And that's because the light is so weak that the electrons zip through one of the slits and we missed it. Those electrons that we do see show no interference. Those that we don't see do show interference. So we're back to where we started. And this is the conclusion, the only conclusion we can draw. And this is a reformulation of what is called the Heisenberg uncertainty principle, which was written mathematically. It's impossible to arrange the light so that it doesn't disturb the pattern whilst at the same time seeing the electrons. We can't do both. So we either see the electrons and we don't see interference, or we don't see the electrons and we do see the interference. So there is a basic limitation on our experiments. They just can't be as delicate as we wish them to be. And what's happening is essentially this. The light is shifting the electrons to where they were, and that shift is enough to destroy the interference pattern. This is a little cartoon that I picked up because people like to paraphrase the uncertainty principle to their advantage. So, I need a description of your project and its projected cost, and this guy's saying it's impossible. This is Dilbert. I love Dilbert. The project uncertainty principle says that if you understand a project, you won't know its cost, and vice versa. So that's just the Heisenberg uncertainty principle. For those of you that love maths, this is how it's written. Delta x is the uncertainty in position, delta p momentum, and it's bigger than this very tiny number, which is 5 times 10 to the minus 35. The reason that we don't observe this weird phenomenon in everyday life is because this number is tiny. And because this number is tiny, this bizarre phenomenon only works at very, very tiny microscopic levels. But we have to accept now that nature behaves this way, in a way that we really don't understand. You might ask any good physicist, what is the machinery by which electrons interfere? How is it that an indivisible particle interferes with another particle and creates a wave? And the answer is we don't know. We just have to accept that nature behaves in the way she does because she does. There's nothing we can do about it. So this is what a philosopher once said, quite pompously, presumably. It is necessary for the very existence of science that the same conditions always produce the same results. But the problem is they don't. Okay, they don't. You may have heard of Schrödinger's cat. So Erwin Schrödinger was another quantum physicist, and he postulated this, that quantum mechanics is a little bit like this. You've got a box with a cat inside it. And inside you've got a mechanism whereby if it trips, the cat gets a lethal dose of radiation and dies. And that happens whether or not you open the box. And it's all completely random. You open the box and the cat's dead. Was the cat dead before or not? Well, this is how weird quantum mechanics is. Quantum mechanics is saying the following. The cat has to be both alive and dead at the same time. Is that an acceptable, everyday, normal thing to imagine? Well, I would say not. Quantum mechanics demands that a particle and a wave pretty much coexist at the same time. And depending on what you do, depending on how you observe your apparatus, it will collapse into one state or the other state. The cat is both alive and dead. And maybe depending on how we open the box, it will collapse into a dead state or an alive state. You think it's bonkers? It sure is bonkers. Okay? But that is the basis of quantum mechanics. Quantum mechanics is nothing like what we can experience in everyday life. It's absolutely mad, but it's the most successful model that physics has ever had for a long time. And it gives us predictable results as well. So we come to the conclusion then that we have to accept that nature at this level behaves in a way that we cannot familiarize ourselves with. And we have to work with these bizarre assumptions that things can be simultaneously one thing and the other. I've got a couple of sweets in my hand, red and yellow. You pick one, it's red. You pick the other one, it's yellow. Quantum mechanics says, I've got a couple of sweets in my hand. They're both red and yellow at the same time. And depending on how you pick the sweet, it's either red or yellow. There's subtle thinking there. It's bizarre thinking, but that's the way it works. Thank you for listening. That's all I had to tell you today, so I hope you enjoyed it. Open to questions if anyone's got any questions at all.
Yeah.
Hello.
With the electrons, you know how they projected onto the black hole?
Yeah.
Would the charges make a difference? Because how could they all have lined up? I didn't understand.
So it's a thought experiment. You can have a board with zillions of detectors on it that can detect the electrons as they arrive. So it might be experimentally impossible to set up, but in a thought experiment, you can set it up with money, no object, and any way you want. But the charge has got nothing to do with it. It's the fact that it's a particle. You could do the same thing with neutrons. You could do the same thing with any small particle at all. Any other questions? So you either understood all of it, or you didn't understand any of it, maybe. I don't know, but it's very odd. It's a very odd concept to come across. Okay, well, thank you very much for listening.